Hello everyone and welcome to yet another informative video from Intellipaat. In today's video, we are going to learn about a fundamental concept in computer science and dynamic programming called Longest Common Subsequence, aka LCS. It is most commonly used in string or sequence comparison. It allows you to identify the longest subsequence, which does not particularly have to be contiguous and is shared by two or more sequences. In this video, we are going to cover everything you need to know about subsequence and LCS in detail. But before we begin, I would like to request you guys to subscribe to our YouTube channel and hit the bell icon to stay updated with multitudes of updates coming from the Intellipaat YouTube channel. Without any further delay, let me quickly list out the agenda for today's video. We will start by understanding what is a subsequence, and in addition to that, what is the longest common subsequence or LCS. Then we'll learn about various approaches to find LCS, which includes recursive approach, memoization approach, and dynamic programming approach. Meanwhile, we'll also be looking into the programming implementations to find LCS between two strings using these approaches. And finally, we'll look into the applications of LCS. And with this, we'll conclude our today's video on longest common subsequence. I hope I have made myself clear with the agenda. So, let's dive into the first topic on our list. What is a subsequence? A subsequence is a sequence of characters or elements that can be formed from another string or sequence of characters by removing some or none of the elements while maintaining the order of the remaining elements. For example, the string ACBACB can have substrings like AC, BA, CB, BAC, CAB, and many more, including ACBACB itself. The common subsequence in the original sequence does not have to be continuous. It can skip elements and appear in a different order than the original sequence and still will be considered its subsequence. So this was all about subsequence, but we are interested in finding the longest subsequence among all these. The longest common subsequence or LCS is the longest subsequence which is common in all of the given sequences. For example, these two strings may have many common subsequences between one another, but the LCS will be that common subsequence which will have the highest number of characters in it. In other words, the longest sequence of characters among all those subsequences will be considered the longest common subsequence. Now, when we know what a longest common subsequence is, let's look into the different methods or different approaches to find this LCS between two strings. The very first approach we'll be going with to solve this problem is using recursion. So here we have our two strings S1 and S2. I have also mentioned their indices over them. I have also written the algorithm here for recursively finding the values of LCS. This will help us in dry running and understanding our recursive approach. So our algorithm starts with checking if S1 of I or S2 of j are /0 or not, which basically means if we are at the end of our strings. Initially, the value of I and j is 0. So we check for S1 of 0 and S2 of 0. We got S1 of 0 as A and S2 of 0 as C. None of them is /0. So we move to the else if part. Here, S1 of 0 is not equals to S2 of 0. So we again move to the else part. From here, our recursion goes in two different ways. On the left, we will be adding 1 to I, and on the right, we will be adding 1 to j. Now before moving on to the right side, we should finish the left side recursion. So we'll proceed with S1 of 1, that is B, and S2 of 0, that is C. Both are neither /0 nor equal. So again, our recursion will get bifurcated in two different directions. On the left, we have S1 of 2, that is /0, and S2 of 0, that is C. And on the right, S1 of 1, that is B, and S2 of 1, that is A. Now looking on to the left side, we got S1 of 2 as /0, so it will return 0. Now moving on to the right, we have got B and A, so again the execution will go two different ways. Towards left, we get S1 of 2, that is /0, and S2 of 1, that is A. And on the right, we have S1 of 1, that is B, and S2 of 2, that is C. Here the left part will return 0 because it has a /0 element in it, and the right part will get bifurcated in two ways again. On the left, we get S1 of 2, that is /0, and S2 of 2, that is C. And on the right, we have S1 of 1, that is B, and S2 of 3, which is also A. Now the left side is having a /0 element, therefore it will return 0. And on the right, we have got a match. So when ith element of S1 is equal to jth element of S2, we again call the function recursively and increment I and j by 1. And in addition to that, we add 1 to the result so that the final call may look like this. Now finally we are at a stage when both S1 of I and S2 of j are /0. So this will return a 0. This 0 will be added to 1 and the result, which is 1, will be returned to the caller. This one will then propagate upwards. Now we are at a place which is formed by the else statement of our algorithm. So in this case, we are supposed to return the maximum of the right and left values, which in this case is 1. Now again, greater of 0 and 1 will be returned. And once again, greater of 0 and 1, which is 1, will be returned. Now when we are completely done with the left side, let's move on to the right side. Here we have got a match. So we will recursively call the function incrementing I and j by 1 and add 1 to the result. Now we have S1 of 1, which is B, and S2 of 2, which is C. Doesn't it look similar to the call we saw while executing the left side? Yes, it is. So the following recursive calls will also be the same, and the returned values will be the same as well. So all this returns us the calculated result S2. This 2 will then be propagated upwards. From here, the maximum of left and right values will be returned, which is 2. And this is the final value of the longest common subsequence between strings S1 and S2. Now, when we have understood the working of this algorithm, let's have a look at the complete code. Over here is exactly that same algorithm which I showed you just now. And we are calling this algorithm from our main function. We have passed the value of S1, the value of S2, and the starting indexes, which is zeros. This values come over here. The algorithm do its work as we saw in the recursion in the try run, and the value is printed right here. So let's run this program and see the output. So it gives us value 2, which is the length of the subsequence. Okay, this was some real big and hectic stuff, right? Well, it really is. The time complexity of this recursive approach is big O of 2 to the power m cross n, where m is the size of string S1 and n is the size of string S2, which can be really very complex and time consuming while working with very large strings. And this is not even the worst part. You remember how we got duplicate recursive calls? Now imagine what would have been the scenario if we had to work with very long strings. We would have come across many such duplicate recursive calls which would not be of any help and just increase the execution time of our program. In order to avoid such issues, we can look for a solution which can store these returned values. In this way, whenever we come across such a situation where things are getting monotonous, we will just avoid the upcoming executions. We call this kind of approach the memoization method. Just a quick trivia, guys. Memoization is derived from the Latin word memorandum, which means to remember, which is frequently abbreviated to memo in American English. And here, in our context, it means to transform the result of a function into something to remember. Memoization is used in computing to accelerate computer programs by minimizing repetitive computations of results and avoiding repeated calls to functions that process the same input. So here we've got our strings once again. Let's quickly proceed in same way we did for recursion. We start with S1 of 0 and S2 of 0. This gets bifurcated in two separate recursions. We first move on with the left part, which again get us to two separate recursions. The left side returns a 0 because it contains a /0 element, but before moving ahead, we will create a table which will hold the records of all these written values. Now we take this returned 0 and store it in our table at the specified cell, which in this particular case is S1 of 2 and S2 of 0. We are done with this left part. Now we move on to the right part, which again gave us two separate recursions. The left part returns a 0, which will be stored in our table. And the right part again gave us two separate recursions. From the left part we get a 0 and we find a match in the right part. So from here we increment the indices of S1 and S2 by 1 and add 1 to the return value. All in all, we get our calculated return value as 1 and that 2 gets stored in our table at the proper cell. This one gets returned to its calling function. Now the greater of the left and right side should be returned to the caller, so 1 gets returned. Notice how we are still storing these returned values into our table at their proper places. Again, the maximum of 0 and 1 will be returned and stored. And once again, we will follow the same rule and 1 will be returned to the caller. With this, we are finished with the complete left part of recursion, and now we move on to the right part. Here, we found a match, so we increment the indices of S1 and S2 by 1 and add 1 to the returned value. Now the point to note here is, we are at a stage where we have already been, and we know that the following steps are simply repetitions. Looking at our table, we see that the cell S1 of 1 and S2 of 2 is already occupied, which is a proof that we have already been at this stage, and the overall value which will be returned by the following recursion is 1. So instead of moving ahead with redundant recursions, we use this stored value, add 1 to it and return it to its caller. Now the maximum of this 1 and 2 will be returned to the main caller. And this final value, which is 2, is the length of the longest common subsequence between strings S1 and S2. Using this memoization approach, we have reduced our algorithm's time complexity from big O of 2 to the power m cross n to big O of m cross n. Implementing this memoization approach using a 2D array without employing a recursive approach takes us to the third way to solve this problem, the dynamic programming approach. We again take the same strings S1 and S2, but this time I am also saving up a space for our resulting subsequence by the name Find LCS. So using this dynamic programming method, we will not only be getting the length of the LCS, but also the resulting LCS string. Since we are not continuing with the previous approach, therefore our program will also get slight changes. So to stay on track while performing the dry run, I've got a code snippet here. So let's start with creating a 2D matrix, where we have S1 in rows represented by I and S2 in columns represented by J. Now according to our algorithm, we start with checking if I or J equals 0, which is true currently because we are starting our program's execution from the top left cell of the table. So this cell will get the value 0. Moving on to the next cell, where the value of I is still 0 but J is 1. This cell too will be getting 0 in it. Looking at the trend, we can understand that all the cells in the 0th row and 0th column will be storing zeros only. Now looking at cell 1,1, we have got the value of I as 1 and J as 1, both of them not equal to 0. So it takes us to the else if part. Here we are comparing S1 of I minus 1, meaning S1 of 0, which is A, with S2 of J minus 1, meaning S2 of 0, which is C. Both of them are not equal, so we move on to the else part. Here we take the maximum of the values which is present in the cell above the current cell and value which is present in the cell which is left to the current cell. So in our case, both of those values are 0. So the maximum will be 0 and it will be stored in the cell 1,1. Moving on to the cell 1,2, it does not satisfy the if part. So we move to the else if part, where we find S1 of I minus 1, meaning S1 of 0, which is A, equal to S2 of J minus 1, meaning S2 of 1, which is also A. We see that the condition in this else if part is satisfied, so we get in and add 1 to the value, which is present in the cell diagonally left to the current cell, and store the result in cell 1,2. Now we have learned the method to insert values into the table, so let's quickly fill up the rest of the values. Along the way, we will be marking those values which have been generated by adding 1 to the diagonal element, like this 1 we got just now. So moving on to 1,3, we find that S1 of 0 is not equal to S2 of 2. So we take maximum of upper and left element. Moving ahead in 1,4, we got S1 of 0 not equal to S2 of 3. We move to the else part and take maximum of upper and left element. Now in 2,1, S1 of 1 is not equal to S2 of 0. So again we take maximum of upper and left element. Moving on to 2,2, we find S1 of 1 is not equal to S2 of 1. So again maximum of upper and left element will be taken. Now moving on to the 2,3, we get S1 of 1 which is not equal to S2 of 2. So we take maximum of upper and left element here as well. Finally, on moving to 2,4, we get S1 of 1 which is B equal to S2 of 3 which is also B. Since we got a match here, we take the diagonally left element, add 1 to it and store it in the current cell. The value of this last element gives us the size of our LCS, which in our case is 2. But our work is not done yet. We are still to find the string of this LCS. In order to do that, we need to backtrack our path from one blue dot to the next, starting from the bottom right dot. We store this last value in a variable named index. Then we come to the part where we declare the character array named Find LCS with size index plus 1. And we assign /0 to the last index of this array. From here, our actual backtracking starts. We start with assigning length of S1 to I and length of S2 to J in form of M and N. Then we enter a loop which will run until I and J both are greater than 0. Inside this, we first meet an if statement which checks if S1 of I minus 1, which is S1 of 1 currently, is equal to S2 of J minus 1, which is S2 of 3 right now. Since they are equal, because both of them are B, we enter this if statement. Here, find LCS of index minus 1, which is find LCS of 1, will get value S1 of I minus 1, which is S1 of 1, whose value is B. After this, we decrement the value of I, J and index by 1. So now in the LCS matrix, we are here, in the first row, third column. Again, starting from top inside the while loop, we check if S1 of 0 is equal to S2 of 2. Since this is false, we move to the else if part. Here it checks if I minus 1 and jth element is greater than I, j minus 1th element. Since 0 is not greater than 1, we move to the else part and decrement j by 1. This will take us here in the LCS matrix. Now we again check if S1 of 0 is equal to S2 of 1, which is true. Both of them stores A. So this A will be assigned to find LCS of 0. Then I, j and index are decremented by 1. This makes the value of I as 0, hence breaking the while loop. Finally, we have got our LCS and the length of LCS. Now let's quickly have a look at the coding implementation of this dynamic programming approach. I've already introduced you to this find LCS method. In here, we create an LCS matrix and add elements in it cell by cell. After this, we have looked into this code snippet. In here, we create the variable index and create a character array named find LCS. And lastly, we had a look into this code where we store the LCS character by backtracking through the LCS matrix. And over here, I'm simply printing the string S1, string S2, the longest common subsequence string and its length. And from the main function, I am passing those values, which is S1, S2 and their lengths. Let's try to run it and see the output. So our string S1 was this, S2 is ABCA, the longest common subsequence comes to be ABC and its length is 3. Now we know what is LCS and how to find it using a C++ program. Let's now have a look into the real-life applications of this concept. We know that LCS can be used to compare two text documents and find the longest common subsequence. This is frequently used in the detection of plagiarism to uncover similarities across documents. LCS is used by spell checkers to offer repairs for misspelled words. Possible fixes can be generated by determining the longest common subsequence between the misspelled word and the dictionary of correctly spelled terms. LCS is used by several compression algorithms such as the Burrows-Wheeler transform to minimize data size for efficient storage and transmission. LCS can be used in music analysis to compare musical sequences, assisting in tasks such as music retrieval, plagiarism detection in music, and melody matching. LCS can help match scanned or handwritten text to recognize letters and words in OCR systems, enhancing text recognition accuracy. LCS is used in version control systems such as Git to identify differences between various versions of a file. It aids in the integration of changes and the resolution of problems. LCS is used in data analysis and database administration to compare records and detect similarities between datasets. It aids in data duplication and integration. LCS can also be used in speech recognition systems to align and match uttered words to know phonetic or word sequences. LCS can be used in data recovery software to recreate partially corrupted or lost files by locating the longest common subsequence between the corrupted data and a reference copy. LCS can be used in NLP to detect common subsequences in sentences or documents, which can help with tasks like document similarity measurement and text summarizing. These are only a few of the many applications of the longest common subsequence in different domains. It is a versatile algorithmic technique used to solve a wide range of issues involving sequence comparison and similarity analysis. That's all we have for this session. I hope now you have got a good understanding of what LCS is and what are the ways to find it while working with multiple strings. Thank you for staying till the end. If you found this video informative, don't forget to give it a like and share it with your friends and colleagues. Also subscribe to our YouTube channel and hit the bell icon to never miss any updates from the Intellipaat YouTube channel.
Just a quick info guys, Intellipaat offers executive postgraduate certification in software development in collaboration with iHub Divya Samparka IIT Roorkee. Through this course, you'll learn a multitude of tools used in the industry such as Git, React, Express, Node.js, MongoDB, and more from the esteemed IIT Roorkee faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of software development.